Welcome back to the Before AGI podcast. We're diving deep into transformer neural networks today.
Really exciting stuff.
Definitely exciting.
Yeah.
Especially for our listeners who are, tech enthusiasts and professionals.
Absolutely. These networks are changing how we interact with technology, especially language.
Like real-time translation.
Yeah.
Those super smart chatbots. Even AI writing tools.
It's fascinating how transformers have become so central to AI.
It is.
Before them, we had models like RNNs and LSTMs.
Right.
But they struggled with speed and context.
I can imagine.
Imagine reading a book one word at a time.
Okay.
You might miss the overall meaning.
Right. It's like trying to understand a joke without getting the punchline.
Exactly.
So transformers came along and they just changed the game.
Exactly. Transformers can see the entire sentence at once.
Okay.
Like grasping a whole page of that book.
Gotcha.
They use self-attention to weigh the importance of each word in relation to all the others.
Okay, so instead of getting lost in the details, they're seeing the bigger picture.
Precisely.
So is that what makes them so much better at things like translation?
Yeah. Let's say you're translating, the European Economic Area was signed in August 1992 into French.
Yeah.
Word order changes, like European economic becoming economic European.
Right.
And then there are things like gender agreement.
Mm-hmm.
A traditional model might stumble,
Yeah.
but a transformer with its attention mechanism can handle these nuances.
That's pretty cool. It's adapting to the specific language and making sure the translation is accurate and natural sounding.
Absolutely.
So this is what's revolutionized things like Google Translate.
This ability to handle long sequences and context has revolutionized it.
So these transformers are really understanding the language.
Yes.
Not just translating word for word.
Yeah.
Our sources also talk about embeddings and encodings.
Yes.
What are those all about?
Think of word embeddings as giving each word a unique location in a multidimensional space. Words with similar meanings are closer together, like king being your queen and ruler, while apple hangs out with banana and fruit.
So it's like creating a map of language where the location of a word tells you its meaning.
Exactly.
But word order matters too, right?
Absolutely.
Apple eat boy. Doesn't make sense.
Right.
Even if the words are in the right semantic neighborhood.
Yeah.
That's where positional encoding comes in.
Yes.
It's like giving each word a GPS coordinate within the sentence, telling the transformer where it fits in the overall structure.
Exactly.
Okay, so they're combining these clever techniques, embeddings, encodings, and this attention thing to really get how language works.
Yeah.
But what's the magic behind this attention? How does it actually function?
Imagine multiple spotlights shining on different parts of the sentence as the AI analyzes it.
Okay.
That's what the attention mechanism does. It allows the model to focus on the most relevant words at each step.
Okay, I'm visualizing these spotlights.
Good.
But how does the model know where to shine them?
It creates 3 vectors for each word: a query, a key, and a value.
Okay.
The query is like a search term.
Yeah.
The key is a tag for each word.
Okay.
And the value is the information associated with the word.
Okay.
The attention score is calculated by seeing how well the query aligns with the keys.
So it's like the model is figuring out which words are most important for understanding the sentence, and that's where it focuses its attention.
Exactly.
And then there's this multi-head attention.
Yeah.
Which is like what?
Which is like having multiple teams of spotlights,
Okay.
each focusing on different aspects of the sentence.
Okay.
This gives the transformer a much richer understanding of the relationships between words.
It's like getting multiple perspectives on a situation, which helps you understand it more fully.
Right.
We've got these encoders, attention mechanisms, spotlights all over the place, but they're also decoders,
Yeah.
right? What do those do?
Think of the decoder as the writer of the transformer.
Okay.
The encoder has read and understood the input, and now the decoder takes that information and uses it to generate an output.
So in the translation example, the encoder is reading the English sentence, and the decoder is writing the French translation using what the encoder has understood.
That's a great way to put it.
So the decoder also uses attention mechanisms.
Yes, it does. It has 2 types.
2 types, okay.
Masked multi-head attention and encoder-decoder multi-head attention.
Okay, more attention, more understanding.
Yes.
But why 2 types?
Masked multi-head attention makes sure the decoder doesn't cheat by looking ahead in the sentence it's generating.
Okay.
It has to predict the next word based only on the words that came before.
Uh-huh.
Then encoder-decoder attention helps the decoder connect the dots between the input and output.
Gotcha.
ensuring the output is relevant and makes sense.
It's like the decoder is checking back with the encoder to make sure the translation is staying true to the original meaning.
Exactly.
It's all about maintaining consistency and accuracy.
It is.
So we've talked about this basic architecture of transformers with their encoders and decoders and attention mechanisms.
Yeah,
But we know there are many different types of transformer models out there,
there are.
like BERT and GPT.
Right.
Before we jump into those specific models, can you help us understand what makes each of these models unique? What are the key variations we should be aware of?
One way to categorize them is by their structure.
Okay.
Encoder only and decoder only.
Okay.
The original transformer we discussed is an encoder-decoder model.
Right.
Good for tasks like translation, where you have an input and a distinct output.
But some transformers only use one or the other. Why is that?
It depends on what they're designed for. Encoder-only models like BERT are amazing at understanding the context of words,
Okay.
which is super useful for things like analyzing sentiment in a tweet or classifying documents.
So BERT is all about understanding the nuances of language.
Yes.
Okay.
And it was pre-trained on a huge data set like Wikipedia.
Wow.
So it's got a vast knowledge base to draw from.
It's like it's read everything. What about those decoder-only models?
Those are the creative writers.
Yeah.
GPT, for example, is the powerhouse behind AI writing tools like ChatGPT.
Right.
It can generate all sorts of text, from poems and code to entire conversations.
So it's like BERT is the reader and GPT is the writer.
A perfect analogy. They both use the transformer architecture, but are specialized for different tasks.
It's amazing how these models are pushing the boundaries of what AI can do with language.
It is.
We got these different types, but how do they actually learn?
Yeah.
What goes into training one of these models?
Imagine giving a model a crash course in all of human knowledge.
Okay.
That's essentially what training involves, feeding it massive amounts of data.
Okay.
The more data it processes, the better it understands the nuances of language.
That it's not just about dumping data on them.
Right, definitely not.
Okay.
The data needs to be pre-processed. It's like teaching the model the alphabet of the language it'll be working with
Okay.
by breaking down text into individual words or subwords. Then comes the training itself, where we feed the model this prepared data, let it make predictions,
Right.
see how well it does, and then adjust its internal settings to get better.
And we've heard these models require a lot of computing power to train. It's incredible how far we've come from those early models that could barely handle a short paragraph.
It's a testament to the advancements in both hardware and software.
Right.
With tools like Run.ai, researchers can manage these intense demands and keep pushing the boundaries of what's possible.
So Run.ai is like a super efficient project manager for AI training.
You could say that.
It helps researchers get the most out of their hardware.
Yeah, especially those powerful GPUs that are essential for training these large models.
It's incredible how much computing power is needed to train these models. Okay, so we've laid the groundwork.
Yes.
We understand the basic architecture of transformers, these different model types, and the general training process.
Yeah.
Now let's dive into some of the specific models that are making waves in the AI world. First up, let's talk about BERT. What makes BERT so special?
BERT, which stands for Bidirectional Encoder Representations from Transformers, was a game changer because it effectively captured the bidirectional context of words. Before, BERT models mostly processed text in one direction, either left to right or right to left. BERT looks at a word in the context of all the words surrounding it, both before and after.
So it's getting a much richer understanding of the word's meaning by considering its entire environment.
Exactly. It's like reading a sentence forward and backward at the same time.
Wow.
Capturing relationships that unidirectional models would miss.
Right.
And because it was pre-trained on such a massive text data set, BERT has a vast understanding of language that can then be fine-tuned for specific tasks.
So it's like BERT has read the library and can now be trained to become an expert in a specific subject.
You got it.
Wow.
Whether it's question-answering sentiment analysis or recognizing named entities, BERT can be adapted to excel at various tasks.
It's remarkable how BERT has become so essential in natural language processing. But there's another model making headlines for its creative writing. GPT. What's the story behind GPT?
GPT, or Generative Pre-trained Transformer, is all about generating text. Unlike BERT, which is primarily an encoder, GPT is decoder only.
So back to our analogy, BERT is the reader and GPT is the writer.
Precisely.
While both were pre-trained on massive data sets, GPT focuses on predicting the next word in a sequence.
It does.
So it's like a super-powered autocomplete.
Yeah.
But instead of just suggesting words, it can write entire paragraphs or even code.
Exactly.
And what's fascinating is its ability to produce creative and original content, not just mimic what it's seen before.
That's right.
It's pushing the limits of what we thought AI could do.
Right.
And there have been several versions of GPT, right?
Yes. GPT-3, and now GPT-4,
Wow.
each bigger and more powerful than the last. They have more parameters. Think of them as the knobs and dials that control the model's behavior and have been trained on even larger data sets.
It's amazing how these models are evolving and getting more capable with each iteration. What are some of the real-world applications of GPT?
It's being used in everything from chatbots and virtual assistants to tools that help people write and even AI-powered art generators.
Wow.
Its ability to generate human-like text is incredibly valuable across many industries.
It's incredible how far we've come with these transformer models. From those early models that could barely handle short sequences to these AI systems that can understand and generate human language with incredible accuracy and creativity.
And this is just the beginning. As these models continue to evolve, the possibilities are truly endless.
That's what makes this field so exciting. We've talked about BERT and GPT, but there's another model that deserves a mention. T5. What's special about this one?
T5, which stands for Text-to-Text Transfer Transformer, takes a unique approach to natural language processing.
Okay.
It treats every NLP task, like translation or summarization, as a text-to-text problem.
Okay.
It converts all inputs and outputs into text strings.
So instead of having specialized models for different tasks, T5 aims to be a jack of all trades.
You could say that.
Whether it's translating languages, summarizing documents, answering questions, or anything else, T5 sees it all as generating text from text.
That's right.
That's pretty ambitious. How does it pull that off?
It combines the strengths of encoder-decoder and bidirectional architectures.
Okay.
It reads the entire input like BERT understanding context, and then generates the output word by word like GPT.
It's like a hybrid of BERT and GPT, taking the best of both worlds.
Exactly.
And it's shown impressive results across a variety of tasks, proving just how powerful and versatile the transformer architecture is.
Yes.
It's incredible how researchers are finding all sorts of new and innovative ways to use these transformers. We focused on how they're used for language, but it's important to remember they're not limited to just that. They're being applied to computer vision robotics, even drug discovery.
That's what makes this technology so fascinating.
The potential applications are vast and still being explored.
Absolutely.
One area that particularly stands out is their use in multimodal tasks.
Yes.
Where the model needs to handle different types of data like text and images.
Right.
What are some of the advancements in this area?
Models like CLAP,
Okay.
which stands for Contrastive Language Image Pre-training,
Okay.
are paving the way for AI systems that can understand the world in a more holistic way.
Okay.
CLAP was trained on a massive data set of text and images,
Right.
learning to connect visual and textual information.
So CLIP can understand that a picture of a cat is related to the word cat.
Yes.
Okay.
And it goes beyond simple associations.
Okay.
It can identify objects in images based on textual descriptions or generate accurate captions for images.
That's amazing. It's like CLIP is learning to see the world through both language and vision. What are the potential applications of these multimodal transformers?
They could revolutionize things like image search, content creation, and even robotics. Imagine searching for images using natural language descriptions.
Wow.
Or having robots that understand and interact with the world through both vision and language.
The possibilities are mind-blowing. We're just scratching the surface of what transformers can do, and I'm excited to see what the future holds for this technology.
I completely agree. It's a fascinating field with immense potential for innovation and impact.
Okay, we've covered a lot of ground in this deep dive.
We have.
We've talked about the architecture of transformer networks, explored different types of model, and even touched on their broader applications.
Yes.
But we've only just begun. Join us in part 2, where we'll take a look at some of the challenges and limitations of transformer networks and discuss what the future might hold for this revolutionary technology.
It really is a paradigm shift in AI, especially for tech enthusiasts and professionals. We're seeing a wave of new applications built on these models.
We've talked about all the amazing things transformers can do. But let's get real for a moment. Are there challenges or limitations with this technology?
Of course.
For example, we've heard these models are really resource intensive.
That's a key point. Like they need...
Training these massive models requires a lot of data and computing power.
Yeah.
which can be a hurdle for researchers or companies with limited resources.
All right.
Remember how we talked about the training process? Feeding the model massive data sets and fine-tuning those parameters?
Yeah.
That requires serious computational muscle.
So it's not just about having a great idea for a transformer model.
Yeah.
It's also about having the hardware to back it up.
Absolutely.
Okay.
Even with powerful hardware, training can take a long time.
Right.
Days, weeks, even months.
Wow.
That's why tools like Run.ai are so important.
Okay.
They help manage the computational demands and optimize resources, making the process more efficient.
So Run.ai is like a super efficient project manager for AI training.
You could say that.
It helps researchers get the most out of their hardware, especially those powerful GPUs that are essential for training these large models.
It's incredible how much computing power is needed to train these models.
Yeah.
But beyond the technical challenges, there are also questions about how these models might be used in the real world.
Of course.
For example, could there be issues with accuracy or reliability?
That's an important consideration.
Yeah.
While these models are powerful, they're not perfect.
Right.
They can sometimes make mistakes or generate outputs that are nonsensical or even harmful. It's crucial to be aware of these limitations, especially when using them in applications where accuracy is critical.
So it's like with any new technology, we need to be mindful of its limitations and use it responsibly. It's not a magic bullet, but it's a powerful tool that needs to be wielded carefully.
Right.
Another concern we've heard is about these models being seen as black boxes.
Right.
We can see what they can do, but it's not always clear how they're doing it.
That's right.
Interpretability and explainability are ongoing challenges in AI.
Right.
It can be hard to understand how a model arrived at a particular output, especially with these complex transformer networks.
Why is it so important to understand how they work? Is it just about scientific curiosity? Or are there practical implications?
It's both.
Okay.
On a scientific level, understanding how these models work can help us improve them.
Right.
But from a practical standpoint, if we're going to use these models in real-world applications, we need to be able to trust them.
Right.
And trust comes from understanding.
So it's like trusting a doctor's diagnosis without knowing anything about their qualifications or how they arrived at their conclusions. We need to be able to see under the hood, so to speak, to feel confident in the decisions these models are making. What's being done to address this black box problem?
There's a lot of active research in this area.
Okay.
Researchers are developing techniques to make these models more transparent,
allowing us to see how they process information and make decisions.
It sounds like there's a push for making these models more accountable and transparent.
There is.
Which is crucial as they become more integrated into our lives.
Yeah.
Okay, so we've talked about some of the challenges. But let's shift gears and talk about the future. What exciting advancements and trends are shaping the world of transformer networks?
Many.
One thing we've heard about is the development of models that can learn from less data.
That's right.
Why is that a big deal?
Traditionally, training these large transformer models required massive data sets, which aren't always available, especially for more specialized applications.
Okay.
But techniques like few-shot learning and zero-shot learning are changing the game.
So it's like teaching someone a new skill with only a handful of examples, or even no examples at all.
Exactly.
Okay.
Imagine being able to fine-tune a language translation model for a new language pair with just a few translated sentences.
Wow.
That's the power of few-shot learning.
That sounds incredibly efficient. What about zero-shot learning?
Zero-shot learning aims to train models that can perform tasks they haven't explicitly been trained on without any labeled examples at all.
Wow.
It's still an active area of research, but it holds tremendous potential.
It sounds like we're moving toward AI that can learn and adapt more like humans do without needing specific instructions for every task. Another trend is the development of even larger and more powerful transformer models.
That's true.
It seems like bigger is always better in the world of AI. What's driving this push for massive models?
There's a strong correlation between model size and performance. Larger models with more parameters tend to capture more complex relationships in the data, leading to better results.
So it's like the bigger the brain, the more it can learn and understand.
That's a good analogy. We're seeing models with billions, even trillions of parameters.
It's mind-boggling to think about the scale of these models. But as we push towards these massive models, it's important to keep those ethical considerations in mind, right?
Absolutely. As these models become more powerful, it's crucial to ensure they are developed and used responsibly.
Okay, so we've got models that can learn from less data,
Right.
models that are getting bigger and more powerful,
Yeah.
and a growing focus on responsible AI.
Yes.
What other exciting trends are on the horizon for transformers?
One trend is the development of more efficient transformer architectures.
Okay.
While larger models generally perform better,
Uh,
they're also more computationally expensive.
right.
Researchers are finding ways to optimize these models,
Okay.
making them more efficient without sacrificing performance.
So it's like finding ways to make these powerful models more compact and energy efficient,
Right.
which would be great for both the environment and accessibility.
Exactly. Another exciting area is the integration of transformers with other technologies like symbolic AI and knowledge graphs.
What's the benefit of combining these different approaches?
Think of it like this.
Okay.
Transformers are great at pattern recognition, but they can struggle with logical reasoning.
Okay.
Symbolic AI, on the other hand, excels at logical reasoning and knowledge representation.
Gotcha.
By combining them, we can create systems that are both intelligent and insightful.
It sounds like the future of AI is about finding the right blend of different approaches, leveraging the strengths of each to create more powerful and versatile systems.
I couldn't agree more.
The field is constantly evolving, and transformers are playing a central role in this evolution.
They are?
As they mature, they have the potential to transform countless industries and aspects of our lives.
Right.
We've covered a lot of ground, from the architecture and variations of transformer models to their challenges, limitations, and the exciting future that lies ahead. But there's even more to uncover. In our final segment, we'll tackle some listener questions that delve deeper into the technical intricacies of these remarkable models. Stay tuned. Welcome back to the Before AGI podcast. We've been exploring this fascinating world of transformer neural networks.
It is fascinating.
These powerful AI models that are behind so many of the advancements we see in technology today. In this final segment, we're going to tackle some listener questions
This is good.
that dive a little deeper into the technical side of things. So buckle up. It's time to get nerdy.
I love getting into the nitty-gritty details.
Yeah, it's where the real magic happens.
Yeah.
Okay, so one question we received from a listener
Okay.
taking the Deep Learning AI course really caught my attention.
All right.
It's about how transformers handle different input lengths. Let's say a model was trained on sentences with a maximum length of 512 words.
Okay.
Can you then fine-tune it on sentences that are only 256 words long?
That's a great question. And it highlights the flexibility of transformers.
Okay.
You absolutely can fine-tune model on shorter sentences. Okay. Even if it was initially trained on longer ones,
Okay.
transformers are remarkably adaptable.
Yeah.
And one technique that helps with this is called padding.
Padding. Okay, I need a little help visualizing that. What is padding, and how does it deal with these varying sentence lengths?
Imagine you have a container
Okay.
that can hold 512 objects.
Right.
If you only have 256 objects,
Okay.
you fill the rest of the space with something neutral.
Okay.
That's padding.
Gotcha.
In transformers, we use max padding to ensure all input sequences have the same length.
Okay.
We add zeros to shorter sequences to match the length of the longest one the model was trained on.
So it's like adding those packing peanuts to protect a fragile item in a box.
Yeah.
They don't change the item itself.
Right.
They just ensure everything fits snugly.
Exactly.
But how does the model differentiate between the actual input and those added zeros?
That's where the intelligence of the attention mechanism shines. It learns to focus on the meaningful parts of the input
Okay.
and disregard the padding. This ability to selectively attend to important information is one of the key reasons transformers are so versatile.
That makes a lot of sense. It's like the model is learning to filter out the noise and focus on the signal. Another question from the same course was about how a single transformer decoder can manage different output lengths.
Okay.
For example, sentiment analysis might need just one output,
Right.
a positive or negative score,
Uh-huh.
while text generation can have multiple outputs,
Okay.
a whole sequence of words.
Another excellent question. Remember, the decoder works one step at a time.
Right.
It predicts the next element in the sequence based on what it has seen before. For sentiment analysis,
Right.
it generates that final sentiment score after processing the entire input.
Okay.
For text generation, it keeps going, generating word after word until it hits a specific end token, indicating the sequence is complete.
So it's like the decoder knows when to stop talking, depending on what it's trying to achieve.
Precisely.
It all comes down to having the right training data and setting up the model to understand the different types of output required for different tasks.
It does.
It's remarkable how much flexibility is built into the transformer architecture.
It is.
It's clear why these models have become so popular and are being used for such a diverse range of problems. But as we wrap up this deep dive, I think it's important to remember that the world of transformers is constantly evolving.
Yes.
New models are being developed, new applications are being explored, and our understanding of this technology is always deepening.
Absolutely.
What's next?
This field is moving at an incredible pace.
Yeah.
It's an exciting time to be a part of it. One trend that's particularly interesting is the research focused on improving the self-attention mechanism itself.
Okay, so like making the heart of the transformer even stronger, allowing it to handle even more complex tasks.
Exactly.
Wow.
And there's also a lot of work being done on developing new training techniques that require less data or make the training process faster and more efficient. The future of transformers is incredibly bright, and I can't wait to see what new discoveries and innovations emerge in the years to come.
I couldn't agree more. It's been a fantastic journey exploring the world of transformers with you. And for our listeners, I hope you've enjoyed this deep dive into this transformative technology. If you're hungry for more AI insights, be sure to subscribe to the Before AGI podcast. And for those of you who are ready to roll up your sleeves and get hands-on with transformer models, I highly recommend checking out my YouTube channel, Ian Ochieng AI. You'll find in-depth tutorials, coding demos, and a whole lot more to help you on your AI journey. Until next time, keep exploring the amazing world of AI.